Hi everyone, I'm Amin and this is another simulation for power electronics control and modulation. So this time I'm going to show you how I did the simulation for the work I put in the description below. The work is about designing an optimized modulation for a two-level three-phase power electronics converter that can actually address the two degradation aspects of SiC MOSFETs. First is the bond wire liftoff fatigue, and the other one is this is the one which is very recently known as gate switching instability (GSI), all in one framework. I'm not going to go into the details of the design. This is actually given in the description in the paper. Uh, I just want to show how I did the simulation in Simulink and maybe get some feedback and comments from you. So here I have, this is my main modulation or control. So this block determines the duty cycles, which are applied to the A, B, and C legs. So these are, I have three duty cycles or three pulses. Obviously for the lower parts, for the lower part of the leg is actually the negate of this pulse. So it's a complementary one. So I need to just determine S, A, B, and C for the upper leg devices. So the way I do that is based on the power losses. So I need to know somehow the power loss values, switching loss and conduction loss of the circuit. So the way I did this in the simulation is this, I used kind of a digital twin here. So this is my digital twin simulating the real system. And so I have to give the currents, the instantaneous values of the uh, phase B, A, B, and C currents with a given constant duty cycle of 50%. So I apply exactly the same switching frequency here, 10 kilohertz, but with the constant duty cycle of 50%. And through this simulation, I can actually calculate the power losses. But these are the power losses for 50% duty cycle. So I have to work out and simply divide it by 50% to get the instantaneous power losses. Because this modulation or this control only needs to know the magnitude of the power losses or instantaneous values of the power losses and redesign the duty cycles accordingly. So maybe instead of this simulation or this kind of block set here, I could use kind of a script, very simple function that gets the values of the phase currents and then calculates the junction temperatures and also the power losses. So because the calculation is based on PLECS library, and I didn't find a very easy way to do that based on a script, so I decided to just put the whole circuit here. Maybe there is another easier way to do that, especially if you want to do this in an embedded system. Obviously, you have to convert everything from this part into C codes, into static libraries. So inside this model, for each phase, I have kind of an edge bridge here. So I have the MOSFETs attached to each other in this way. So I have two MOSFETs. I put just simple switches over here and also one controlled current source. So the current is actually given from outside. I measure the current of the system. I apply it here. And based on the signal, the gate drive, I get the values for power losses. So they're actually given through these probes here. So each one is actually calculating the conduction loss for each switch and also the switching loss. And this is actually averaged over the switching period. That's why I need to recalibrate it to get the uh, value of the power loss. And these are the heat sinks with thermal resistance, capacitance, and also the DC voltage here. So this circuit basically calculates the power losses, conduction and switching loss for each switch. So overall, you will have signals of 12 signals coming out from here. And then inside this control modulation, I calculate the optimized duty cycles. I give the pulses to the main circuit. The main circuit is simply the two-level three-phase power converter. So with exact values of the heatsink and MOSFET and so on. So everything is exactly the same as I use in the model. So for example, I use this part number for the MOSFET. and I have RL load here. And through these measurements, I capture the values for currents, and then I actually fit them back into the model here to update the power loss values. So what happens inside of this control modulation? So I apply the magnitude or modulation index of the space vector modulation and also the frequency 50 Hertz. And inside, it's actually a bit complicated, but I have two different modulation techniques. So let's focus on the one I use now. This is the S function. So inside this S function, I have a script written as MATLAB S function. And inside, I'm using an optimization solver called CVXGEN. I will put the link in the description how to use that in MATLAB. This is actually developed by Stanford. It's quite fast, can quickly solve QP problems, small QP problems. And through that optimization, I determine the duty cycles such that the overall thermal stress is minimized. And then these duty cycles are applied to this variable pulse generator, given the duty cycle and also the constant switching period, which then are applied to the main system. The input to this S function is the power loss values and also the desired voltage vector, which is coming from outside. You see, this is the magnitude, this is the frequency, so you can simply work out the phase from here. This is the phase, integrated frequency, multiplied by cosine and sine to give you the real and imaginary part of the voltage vector. So the desired voltage vector in imaginary and real part, as well as the power loss values, conduction and switching loss, are all given into this S function. And as I said before, the way that I calculate the power losses, especially for conduction loss, is that because they're already averaged out over the switching period by PLECS, I have to scale them by 1 over d and 1 over 1 minus d for the lower legs and for the upper leg to get the value of the peak of the power loss, and then recalculate my desired optimized duty cycles. Up there, I have this built-in MATLAB space vector modulation 2-level to compare the results with and to see how it works. So this is a simple mechanism to calculate the duty cycles. Maybe I could actually look under mask and put this inside, but I put it actually outside after computing the pulse waveform. So going back up, and I have actually put a switch here to select different modulation techniques. So now it's actually on my reliability optimized SVM, but you can simply switch and it changes the key here. So we can compare it with the SVM from MATLAB or use this optimization method. And inside, as I said, you have your 2-level 3-phase power converter sitting here, measuring everything, power losses and junction temperature to capture and record into a file. So simple as this. So now let's run the simulation and see what we get at the, for example, the phase current. Have a look at the phase current. Here's the scope. Yeah. So basically it should generate exactly the same phase currents as you expect from the conventional SVM or from the MATLAB's SVM, because generating the desired voltage, the real and imaginary part, are actually imposed as hard constraints in the optimization. So it should fulfill the desired voltage reference. So this is the current profile of phase A, is going up and down between minus 25 to 25 amps. Yeah, thank you very much for watching this video and let me know your comments, feedback on this simulation. Thank you.